Two more properties that we want to talk about discrete time convolution. One is what happens when you convolve a discrete time signal with an impulse. It turns out that that basically just shifts the signal that you're convolving with the impulse to the location of the impulse. And I also want to talk about the width property. But let's go ahead and start with the convolution with a discrete time impulse. So discrete time convolution with an impulse. So what happens? So we want to compute h of k convolved with delta of k minus m. So this delta function is just a delta function located at m on the time axis. And if I write down the definition of discrete time convolution, it's this discrete time sum. The sum from n equals minus infinity to infinity. The first signal in my discrete time convolution is h, so I've replaced the time variable k with n, my counter variable. And then the second signal in my discrete time convolution is delta of k minus m. So I have left the argument k minus m alone, and I've tacked on a minus n. That's how we write down discrete time convolution. If you look at this, all of the terms in this sum are 0, except for when we're at time our counter variable n is equal to k minus m, because the delta function is 0 everywhere except at one point. So this sum, even though it has an infinite number of terms from minus infinity to infinity, all of them are 0 except for one of them. So really what this sum looks like is a sum of 0 plus 0 plus 0. Finally we get to the time, or the counter variable, when the counter n is equal to k minus m. We have a non-zero term, then we have a whole bunch of other terms. So if I replace n with k minus m, what I end up with is h of k minus m, because n is equal to k minus m. And then the delta function, which is delta of k minus m minus n. When I replace n with k minus m, I just have k minus m minus k minus m. So that's really my signal, h, k minus m times the delta function at 0. Well, we know what the delta function of 0 is equal to. It's equal to 1. So this is just equal to h of k minus m. So what we've just shown is that when I convolve a signal with an impulse that's been shifted to time m on the time axis, what I get out is my signal shifted by amount m. So this is what we mean when we say that discrete time convolution with an impulse places the signal at the location of the impulse. Let's talk about the width property now. The width property says that if I have a signal h1 that has length m and a signal h2 of length n, when I convolve them to yield some new signal c, then the length of c is m plus n minus 1. So let's show that that's true. So let's look at the width property of discrete time convolution. h1, we're going to say, is a finite length signal, has length m, and just to make things simple, let's picture that as being a length m signal starting at 0 up to m minus 1. So this is a signal that starts at time 0 and goes up to m minus 1. Similarly, h2 is going to be a finite length signal of length n, and also just to keep things simple, we'll assume that it starts at 0 and goes up to time n minus 1 on the time axis. And what we want to know is what is the length of their convolution. If I convolve h1 with h2 to get this new signal c, how many elements does c have that are non-zero? What is the length of c of k? So, one thing that we know is we know how to easily compute the start time and the stop time of c of k. Just like for continuous time convolution, the start time is given by the sum of the start points and the stop time is given by the sum of the stop points. So if we wanted to compute the start time for c of k, I'll call that k start, well that's just equal to 0, the starting time of h1, plus 0, which is the starting time of h2, which gives us 0. So ck is equal to 0 for all time less than this. So when k is less than 0, we know that c of k is going to be 0. But it's going to kind of turn on, in essence, at k start equals to 0. We can do the same thing for the stop time. At what point do we know that ck will stop being on and turn off, be 0 for some time and up? Well, same type of computation, k stop is just going to equal m minus 1, which is the stop time of h1, plus n minus 1, which is the stop time of h2. And if you add these together, you get m plus n minus 2. So the last possible time that c of k could be on is m plus n minus 2. So for any times larger than this, we know that c of k is going to be 0. So we now know that c of k is 0 for k less than 0, and it's equal to 0 for k greater than m plus n minus 2. So what is the length? Well, the length is always the endpoint minus the start point plus 1. So let's do that computation. The stop point is at time m plus n minus 2, minus the starting point, which is 0, plus 1. So that gives us m plus n minus 1. So that right there is the width property. We just showed that C of k now has a length of m plus n minus 1, like we wanted to.